Welcome to the deep dive. Today, we are undertaking a pretty critical mission, giving you the ultimate distilled shortcut to the foundational math of chemistry. We are going deep into Chapter 3, which is all about atoms, molecules, and the essential calculations they call stoichiometry.
That's right.
This is really the engine room of quantitative chemistry, and mastering this deep dive means you have the universal toolkit for everything that comes next.
It absolutely is the toolkit. I like to think of this stuff, the mole, the mass units, the formulas, as the universal language that translates that invisible world of atoms into things we can actually measure.
And control in the lab.
Exactly. So if you've ever felt a bit overwhelmed by conversions or balancing equations, we're going to unpack these core concepts systematically.
Okay, so where do we start?
Right at the very smallest scale, how we actually measure mass. Okay, let's unpack this. Hashtag 3.1 masses of atoms and molecules.
Right, so you can't just put a single atom on a scale, obviously. Scientists had to come up with a benchmark.
A standard. And that standard is the unified atomic mass unit, or just U.
And that's defined as exactly 1/12 of the mass of a carbon-12 atom.
Right.
Why carbon-12 specifically?
Well, it's stable, it's abundant, and it just became the standard that the whole periodic table is based on. You might also hear U called the Dalton, or day, by the way.
Okay, so that unit, U, gives us our first key calculation.
Relative atomic mass, which we call R. R is the ratio of the average mass of an element's atoms compared to that unified mass unit.
And the interesting thing here is that R is almost never a nice whole number.
And that's a direct consequence of nature. It tells us something important.
Okay, so this is the classic example, like chlorine.
Exactly.
Everyone learns R is 35.5. And that's because most elements are actually mixtures of naturally occurring isotopes.
Atoms of the same element, just with different numbers of neutrons. So that 35.5 for chlorine, it's just the weighted average of its two main isotopes, chlorine 35 and chlorine 37.
And because R is a ratio, you're comparing two masses, the units just cancel out, so it's unitless.
Precisely. Which is a little different from relative isotopic mass, which is simply the mass of one specific isotope. So carbon-13 is just 13.
Okay, so then when these atoms bond together, we use that R data to find the mass of the whole compound.
Right. We calculate the relative molecular mass, or Mr., just by adding up all the R values.
So for something like methane, CH, you've got one carbon at 12.0, plus 4 hydrogens, which are 4 times 1.0.
Gives you 16.0.
Simple enough.
And we do make a small but important distinction in terminology here. We use Mr. for simple molecules like methane, but if the substance is ionic or has a giant covalent structure,
like silicon dioxide, SiO,
or magnesium hydroxide, MgOH, we technically call it relative formula mass. But, and this is the key, we still use the symbol Mr. and calculate it in the exact same way. For MgOH, that would be 58.3. Hashtag type 3.2 hydrated and anhydrous compounds.
Okay, moving on from sort of abstract atoms to compounds you can actually see in the lab. Sometimes water gets trapped inside the crystal structure itself.
Yeah, we call that water of crystallization.
So a compound that contains this water is called a glot.
A hydrated compound. The classic example is that beautiful blue copper sulfate, CuSO5H.
And in the formula, that dot separates the salt from the water molecules, right?
It does. It tells you exactly how many moles of water are locked in per mole of salt. And if you heat that blue salt, the water evaporates, it turns into a white powder.
And that white powder is the anhydrous compound, just plain CuSO.
Exactly.
The Gallerchange is such a great visual for the concept. So when you're calculating the Mr. of a hydrated salt, you have to be careful.
You really do. You have to treat the water of crystallization separately. You find the Mr. of the salt part, the CuSO, and then the Mr. of all the water, the 5H, and then you add those two big numbers together.
And this whole process is reversible, isn't it?
Completely reversible. You heat it to dehydrate. You just add water to rehydrate it. It's a really essential process in the lab. Hashtag tag 3.3 accurate relative atomic masses via mass spectrometry.
So we just said R is an average mass.
Yeah.
But, how do we get such incredible accuracy for those averages?
Well, this is where technology steps in. We're talking about the mass spectrometer.
The mass spec.
Yep. It's basically a super high-tech sorting machine. It vaporizes your sample, blasts it with electrons to make charged ions
And then it uses electric and magnetic fields to separate those ions.
based on their mass-to-charge ratio, the Me ratio.
Okay, and the result is a graph, the mass spectrum. Relative abundance on the y-axis and that Me ratio on the x-axis.
Right, and for ions with a single positive charge, that Me value is pretty much just the isotopic mass.
So you can use that spectrum data to calculate a really accurate R.
It's a three-step process. You take the mass of each isotope, multiply it by its percentage abundance from the graph, add all those values up,
And then divide the whole thing by 100.
and you're done. For an element like neon, that gives you a precise R of 20.2.
But this is where it gets really, really cool, especially for organic chemistry.
Oh, absolutely. It's the ultimate chemical fingerprinting tool.
So the peak with the highest Me ratio, that's the molecular ion peak, or MO.
And that peak is the entire molecule, just missing one electron. It instantly gives you the relative molecular mass, the Mr. of your compound.
But those electrons flying around don't just ionize the molecule.
No, they often smash it apart. That's called fragmentation. So all the peaks that are lower than the monomer peak represent these smaller pieces.
It's like molecular detective work.
It is. If you look at propanone, the Mi peak is at 58.0, but you'll also see big fragment peaks, one at an ME of 15, which is a methyl group, CO where, and another at 43.
Which could be the acetyl group, Chaseco.
And we can get even more detail from the tiny little peaks next to the main word.
You mean the M+1 peak?
Exactly. That's there because of the naturally occurring carbon-13 isotope. There's a specific formula you can use with the ratio of the M+1 peak to the MAM peak to figure out exactly how many carbon atoms are in your molecule.
Wow. And then there's the M+2 peak, which is a dead giveaway for halogens.
An absolute giveaway, because chlorine has two common isotopes, OCl and SCl, in about a 3-to-1 ratio.
The M peak and the M+2 peak will have a height ratio of 3.1.
And for bromine, which has two isotopes in a nearly 1-to-1 ratio.
The M and M+2 peaks will be basically the same height, a 1.1 ratio. See that you know you have bromine? It's incredible.
So we've spent all this time talking about the mass of single atoms, which we can't measure directly. So how do we scale up to something we can actually weigh in a lab?
The answer is the king of chemistry, the mole.
The mole is the bridge. It's defined as the amount of substance that contains a specific number of particles.
That number being the Avogadro constant, L or Na, which is $6 or $2.02 12.
Right, and that can be atoms, molecules, ions, electrons, whatever you specify.
It's just such a mind-bogglingly huge number.
It is. So the mass of 1 mole of a substance is its molar mass, M.
And the numerical value is the same as the R or Mr. we just talked about.
But now it has units. Grams per mole. G a mole.
Which leads us to the core relationship, the one formula everyone needs to know.
Moles equals mass in grams divided by the molar mass.
And a really crucial detail here for problem solving.
Yeah.
You have to be super specific about the particle you're counting.
Oh, absolutely. 1 mole of Coyo molecules contains 2 moles of clay atoms. You have to be clear, or the calculation goes wrong from the start. Hashtag Tech 3.5 mole calculations, stoichiometry.
And that brings us neatly to stoichiometry.
Which is really just the fancy name for studying the mole ratios in a balanced chemical equation.
The big numbers in front of the formulas, the coefficients, they give you the ratio of reacting moles.
Yeah, so in the reaction FeO plus 3CO plus 3CO Phe, the ratio is 1 to 3 to 2 to 3.
And that ratio is so important when you're dealing with limiting and excess reagents.
Right. In a real experiment, you'll always have one reactant that runs out first. That's your limiting region.
And it's the one that determines the absolute maximum amount of product you can possibly make.
Exactly. The reactant that's left over is just an excess. And to find the limiting one, you have to convert the mass of each reactant to moles and then compare that ratio to the one the equation demands.
You can also work backwards, can't you? Use known masses to figure out the stoichiometry of an unknown reaction.
Yep. Find the simplest whole number mole ratio to figure out the coefficients for the balanced equation.
Okay, before we get to more formulas, a quick word on calculation precision. This is a big one.
It's a golden rule. Your final answer should have the same number of significant figures as the least precise piece of data you started with.
But, and this is so critical, do not round any numbers until the very end.
Don't do it. You'll introduce rounding errors and lose marks.
Okay, so stoichiometry also lets us define the makeup of a compound, like percentage composition by mass.
Right. The formula is just the total R of the element you're interested in, divided by the Mr of the whole compound times 100. So for iron oxide, about 69.9% of its mass is iron.
And since no experiment is ever perfect, we need to calculate percentage yield.
That's just your actual yield, what you actually measured in the lab, divided by your predicted yield from the stoichiometry.
Times 100. It tells you how efficient your reaction was.
Exactly. And finally, we use moles to figure out chemical formulae.
The empirical formula, or EF, is the simplest whole number ratio of atoms.
Whereas the molecular formula, MF, is the actual number of atoms. To find the MF, you find the mass of your EF, divide the known mixture of the compound by that EF mass to get a multiplier.
And then you multiply everything in the empirical formula by that whole number.
Yeah.
Hashtag 3.6 chemical formulae and chemical equations.
And of course, all these calculations fall apart if you don't have the correct formulas and balanced equations to start with.
For ionic compounds, the main rule for the formula is that the positive and negative charges have to balance out. The whole thing has to be neutral.
And you can predict a lot of charges from the periodic table. Group 1, 2, and 13 metals are +1, +2, +3.
And nonmetals in groups 15 to 17, their charge is 18 minus the group number.
But you do just have to memorize the common compound ions.
Nitrate, no eros, sulfate, SO-oros, ammonium, and H.
And so on. For transition metals with variable charges, we use Roman numerals, like iron 2 versus iron 3.
Then, for balancing the full equation, there are two unbreakable rules. First, atoms are conserved.
Can't create or destroy them.
And second, you absolutely cannot change the chemical formulas. You can only put coefficients in front.
Right. And a good tip for combustion reactions is always balance carbon first, then hydrogen, and save oxygen for last. It just works.
So for that iron oxide reaction, fluoro needs 3CO to make 2Fe and 3CO. Then we add the state symbols.
S for solid, L for liquid, G for gas, and AQ for an aqueous solution.
And if the reaction happens in water with ions, we can simplify the whole thing down to an ionic equation.
We do that by getting rid of the spectator ions.
The ones that are just floating around watching.
Exactly. They don't change their state or their charge. So you write out all the aqueous ions, cancel out the spectators from both sides, and you're left with just the particles that actually reacted. Hashtag tag 3.7 solutions and concentration.
Okay, let's switch gears to working with liquids in the lab.
Concentration.
It's defined as the amount of solute in moles dissolved in 1 cubic decimeter of solution. So that the units are mole dA.
And a classic trap here is the volume conversion. Your lab glassware is probably in cubic centimeters CMA.
You have to divide CMA by def5UN to get DMAA before you use the formula.
Which is concentration equals moles divided by volume in DMA.
The key procedure that uses this is titration. It's how you find the exact concentration of an unknown solution.
A titration problem always has 5 key pieces of information.
The balanced equation, the volume and concentration of the solution, and the volume and concentration of the one you don't know.
You need 4 of those to find the 5th. And the process is very systematic. First, calculate the moles of the known stuff. Second, use the stoichiometry to find the moles of the unknown.
And third, use the volume of the unknown to calculate its concentration. It's a perfect mix of lab work and calculation. Hashtag 3.8 calculations involving gas volumes.
So what about gases? They're a bit different.
Thankfully, Avogadro's hypothesis makes things a lot easier. It just states that at a constant temperature and pressure, equal volumes of any gas contain an equal number of molecules.
Which leads directly to the idea of molar gas volume. At room temperature and pressure, or RTP, 1 mole of any gas.
Helium, oxygen, doesn't matter.
Occupies a volume of exactly 24.0 dmol.
So for reactions involving only gases, the mole ratio is the same as the reacting volume ratio. That is a massive shortcut.
It is. You could figure out the formula of an unknown hydrocarbon just by measuring the gas volumes when you burn it.
Okay, give us an example.
Let's say you burn 50 centimeters of propane with 250 centimeters of oxygen, and you make 150 centimeters of oxygen, and you make 150 centimeters of Gordo. The volume ratio, 50 to 250 to 150, simplifies down.
To 1 to 5 to 3.
So if 1 part propane makes 3 parts AO, the propane must have 3 carbon atoms. It's C something. You use the oxygen to figure out the hydrogens and balance the whole thing. Hashtag tag outro.
Wow. Okay, so we started with the tiniest possible measurements, the R, and we've ended up applying stoichiometry to liquids and gases.
We really covered the 3 major pillars, didn't we? Measuring and identifying things with mass standards and mass spec.
Then using the mole to calculate yields and formulas.
And finally, applying all of that to solutions and gas volumes.
So your mastery of this chapter is really your mastery of translation.
That's a great way to put it. You now have the knowledge to translate the invisible world of atoms into the precise, measurable reality of the lab.
Whether that's reading a mass spectrum or doing a perfect titration.
The mole is the language, and stoichiometry is the grammar that lets chemists predict and control what's going to happen in a reaction.
So what does this all mean? The constants we've defined today, the mole, the R, the molar gas volume, they are the absolute bedrock of chemistry and practice. Your ability to use stoichiometry gives you the power to fine-tune any reaction, from making something in a factory to just preparing a solution in a flask. Now go forward and calculate something. A warm thank you from us for joining this deep dive.